Sorry, I have some problems with recording, so let's go back. So we talked about buoyant force, and that buoyant force is can be shown that this buoyant force it is equal to the density of water to the gravitational acceleration g and the volume of object. So how this equation can be developed is that we can see here that F buoyant is F bottom minus F top. So we can write that F bottom is what? Is the difference between two hydrostatic pressures. So this F bottom would be, let's mark this to three parts. Let's mark H2. That be H2 would be here, this height. So this would be H2. This would be height would be H1. So this smaller one, okay? H1 and H2 is the bigger one. So F bottom is what? F bottom is, can we write in terms of hydrostatic pressure? So hydrostatic pressure is would be for F bottom. So till the bottom is, let's say, where this cube is. So H2 contributes to the end of this cube in the, just slide down this cube, okay? So rho G H2 stands for pressure of hydrostatic pressure. So this hydrostatic pressure times surface area would be force minus rho G H1. Now F top is with H1 because the water, this red water that was above this top is putting the weight on this cube's top wall. So times surface area. And now what we see here that these two surface areas, we can simplify this calculation. So we write surface area, then we write rho G H2 minus rho G H1, and we can write also write surface area. Sorry, again, surface area has to be A, capital A for you here. In Lithuanian would be S. So it is A. So surface area here it is A. Now it is what it is along with the surface area. Rho and G may go out of the brackets. So A, rho and G. Here would be H2 minus H1, and it would be A rho G delta H, and would be what? Delta H times delta A would be rho G delta volume. So this volume is the volume of the object and therefore, because we don't need this delta, we can may get in simplified situations, we may get rid of this. So there it is, rho water, g, and volume of the object. So this is the buoyant force. And as we told, that the buoyant force depends on the volume of the object. If we put the chunk of heavy metal to this water, if the water level was here, then the water level, it increases to this point. So the chunk of that metal tends to displace the water. Again, water tends to come back here, come back to its place and push this chunk of metal up. But now it depends whether this displaced, the volume of that displaced volume is sufficient to produce that buoyant force. If it is sufficient, then this object floats. So that's why if this chunk sinks, then we expand the volume of the object. So if we expand the volume on the object, because buoyant force depends on the volume of the object, then it may this chunk transform to ship form where it has air, so the volume increases. Then it may float, and that's why metal ships, they float, although the chunk of metal it sinks. So another one thing that we were seeing here with the forces, so we wrote, if F buoyant force equal to F gravity, the object floats at any depth. So now we can write that here F buoyant force, this F buoyant force is equal to F gravity. So now what is happening here, this buoyant force is equal to gravity force. So we can write that what is the buoyant force? Buoyant force is rho of water, g, v object, and we can write again that gravity is what? Gravity is rho of object times v of object, because it's mass, yes, and g, acceleration due to gravitational force. So we can cancel out v object and we can cancel out g, and we see that rho water is rho object. So it means densities matter. So because densities, they incorporate volume, yes, because density is mass divided by volume. So in case of this, we can write that F buoyant, for object to float at any depth, rho, we can write, maybe have red pen, we can write that this we can rho liquid density, it has to be equal to density of object. Here we can write that density of liquid has to be higher than density of object. And here we can write that liquid is density of liquid is lower than density of object. So then it sinks. Okay, so this is it. Now we can speak about, so far we have been speaking about fluid statics, so we can speak about fluid dynamics now, and fluids. So fluid dynamics. Fluid dynamics. So imagine that the water is flowing. Water is flowing out of the faucet. Let's say the water is going down here. So how to measure the rate of the water? So the rate of the water, so capital Q of water, can be measured by volume change in volume divided by change in time that it occurs. So it can be measured as, usually it is measured by we can use this measurement, cubic meters per second, or we can use liters per second. So also this Q water can be expressed as U times A. So U in this case would be speed, A would be surface area. Surface area would be meters per second. Surface area would be meters squared. And when you multiply these things, meters and meters squared, you get cubic meters, the same as this, and you get seconds. Because here it is divided by 1. So this is the volume flow rate. Volume flow rate. And now what causes water to flow? Water needs force to flow. Water needs force to flow. Why? Because water, there is intrinsic friction inside the water. It is called viscosity. So this, because when water flows or liquids flow, so intrinsic friction in liquids is viscosity. Viscous liquids, water is not that viscous liquid, but ketchup and syrup, they are high viscosity liquids, so they flow very slowly because they have high viscosity. And when liquid flows, it flows, let's say we have this a pipe, here it is a pipe, and liquid flows in layers. It's visualized like streamlines. So the middle layer flows, this flows with the highest V max, highest speed. These two layers of liquid, they flow in lower speed. These have V lowest. So this is V middle speed. So this is because the water and also other liquids in itself, they have intrinsic friction. It's called viscosity, because when molecules flow in this streamline, they have friction with these molecules here in this streamline. So between those streamlines, they are slowing each other down. There is friction force in this direction, friction. So they are slowing each other down. Therefore, in order for the liquid to move in V constant, we need F, let's say push, to be equal to F friction, because there is already intrinsic friction inside this liquid. So therefore there is example like we have water towers. They are above, at higher heights. So and the water goes down from this water tower. It goes down because here hydrostatic pressure yes, we can say that because of, simply saying, because of gravity, this water tends to go down. So in this case, the force that making the water to flow down from this water tower would be gravity pressure, would be due to gravity. And now, therefore, this force allows to overcome friction. So another thing would be continuity principle. So continuity principle, if we have, let's say, a pipe, so the amount of water that comes in must go out. There are no accumulations of water anywhere here, so what comes in must go out. It seems that this holds also for the pipe with restriction. Here is a wider pipe, bigger cross section. Here is smaller cross section. So here we have A1, here we have A2. The same applies here because there are no accumulations during the experiments. There are no accumulations. So initial speed U1 and the speed that the water goes out is U2. So as we know that Q water 1, let's say at this point, the rate should be equal to Q water 2. So we can write this as U1 A1 U2 A2, like we did in here, U and A, yes? And it means if this continuity principle holds is true, and it is true, because there is no water accumulation anywhere, so it means that if U increases, let's say if there is U1 and A1, so it's something, and A2 decreases, cross section decreases, so what happens? U2 has to increase. So it means that at narrower pipe, restriction, we may call it restriction here, the speed of flow increases. So if there is narrower pipe, the pipe is wide and suddenly it becomes narrower. So it restricts the water's motion, and the speed has to increase in order for no accumulation to occur. So this is continuity principle. Now, the last thing I want to tell you is Bernoulli's equation, and it tells why planes fly. So as you remember that total energy, mechanical energy, was kinetic energy plus potential energy, and it was constant. Now we can, it's easier to show Bernoulli's equation using E total. It would be using thermodynamics. It uses internal energy. So U plus EK plus EP. So this is kinetic energy. This is potential energy. This is internal energy. Internal energy is, it is associated to the substance, let's say, inside some kind of, if we have let's say a box, and we have some kind of molecules inside there, so these molecules have these gases, gas molecules have kinetic energy. They also have some kind of potential energy due to orientation within each other, and they also have kinetic energy. So they have energy inside them, because they may be, if it's we may burn them so we can obtain some work. So some kind of material itself has some kind of energy. Also this box has some kind of energy, because it's also solid, we can burn it. So this is internal energy. We'll deal with a bit more in thermodynamics, but what I wanted to show is that this E total can be written in terms of internal energy, can be written as this would be atmospheric pressure times delta volume, because the philosophy behind this is, in order to create this box with these gases, this volume, change in volume, let's say from nothing, from a scratch, you have nothing, just in the space, just some kind of dot, and you need to create, just like practically, you need to create some kind of thing, let's say device, appliance, or something. Just you need to create, so it has to take some room in the space, so it has to get some kind of volume for a thing to exist. It has to take some volume, and this volume must be given when the atmospheric pressure is against your how to better explain it. Atmospheric pressure is you have to do some work against atmospheric pressure, because atmospheric pressure tends to reduce this volume, so you have to atmospheric pressure tends to reduce this volume, and you need to do work against atmospheric pressure to expand the system. So this is the energy corresponding to creation of the system. And also kinetic energy is half mass speed squared, and mgh is potential energy due to gravitation. So what you need to do to obtain pressure from energy. So if you have pressure, if it's F divided by area, force divided by area, so you can multiply up and down of this equation by h. If you multiply by h, by constant, nothing happens. So then you can write what? F is mg times h, and this is a times h. And here you have potential energy divided by volume. So you see that you have potential energy divided by volume. So in order to obtain pressure, you need to divide potential energy by volume. Okay, so that's what we do. So we have E total, we have P delta V plus mv squared divided by 2 plus mgh. So we divided everything by volume, and we get total pressure. Here we can write delta V, doesn't matter delta this time, because let's say it's expanded from 0. We have here P, this was atmospheric pressure, plus mv squared 2 times V. Here we have plus mgh divided by V. What do we get? We get P atmospheric plus mass density times volume, speed squared 2V plus mgh divided by volume. And then we can write that P total is atmospheric pressure plus, here we get rho V squared divided by 2 plus rho gh. So this is atmospheric pressure, this is hydrodynamic pressure. Hydrodynamic pressure This is hydrostatic pressure. So atmospheric pressure, we know what it is. It is due to atmosphere is attracted by gravity. This is hydrodynamic pressure. In hydrodynamic pressure, it is associated with kinetic energy. You see that we have derived it from kinetic energy. It is explanation is that I will write this equation again. So hydrodynamic plus rho GH. It is hydrostatic. What we know, this one we know. As hydrodynamic, let's say we have a pipe and we have molecules. Molecules are moving with the velocity v. So these molecules, as the flow of the fluid, they can move an object. If there is some kind of object, can move it, or they can turn the, if we have energy station, let's say hydro energy station, so it can move the turbine. So it is associated with moving object having kinetic energy. Also water is moving, it has kinetic energy, and it can push. If there is an object, some kind of object in it can push this object and make it move, perform work. So it is associated with kinetic energy and pressure that moving water exerts on the object. Let's say it gets pushed because the water exerts pressure on some kind of object that is in its way. So okay, now so this is called Bernoulli's equation. Bernoulli's equation. So what does it say? It says that if we have a pipe that is becoming narrower, we have a pipe, and this is if here we have speed, velocity in this case, or speed, doesn't matter, we have low by continuity equation, we know. So here we have speed high by continuity equation. So it means that in this case, if P total is constant, this has to be constant. So hydrostatic pressure we may neglect it in this time. So because we can say that it is the same in the same here and the same here, but atmospheric pressure and hydrodynamic pressure, they are the same that matters. So here velocity is low, here velocity is high. So at narrower pipe increases, velocity increases, because total pressure has to be constant. So atmospheric pressure and hydrodynamic pressure, they have to be the same everywhere. So in order here for hydrodynamic pressure to increase, so hydrodynamic pressure increases here, because V increases here, and here it is V. So hydrodynamic pressure increases, hydrodynamic pressure increases. Therefore, atmospheric pressure, so here we are restraining ourselves to only P atmospheric plus this guy, plus hydrodynamic. So hydrodynamic pressure increases here because speed increases. So therefore, P atmospheric decreases. In this case, it was P atmospheric was normal, and hydrodynamic pressure was lower compared to this. So when there is a restriction, where the pipe is narrower, so then hydrodynamic pressure increases because the speed increases. So that's what gives the so that's why what gives the lifting force to the planes. And if there is the wing of a plane, so the wing is bent on this upper side, and when the air goes through this wing, so the air goes above the wing and below the wing. So what happens now? Because here it is length, here it is bigger as because it is bent, so there is bigger length. Here the length is shorter, small l. So because there are no accumulations of water or any other liquid, as we have seen already, so then it means that Q1, Q2, they have to be equal. So in order for them to be equal, what was like in that pipe explanation, so speed here, speed V1 has to be bigger than V2. So V1 has to be bigger than V2, because in order for the air to travel, air goes here, here, and here, to travel this direction, to travel this longer length, this is L big, this is L small, at the same time, so we divide by T, and we divide by the same T. So here we get, because capital L is longer, we get that V1 has to be more than V2. So we used U in previous case, so it doesn't matter V or U, so U is the speed and V is the speed, so it is the same. So has to go in longer, so therefore this V is higher. So because according to Bernoulli's equation, we understood that when the fluid flows in high speed, then the pressure is reduced. So therefore this pressure here goes down in this fluid. This flow can be produced by the engines, of the plane. So pressure P1 is here, pressure P2 is here. So P1 is lower than P2, and therefore this difference in pressures produces lifting force. So lifting force, and that's why the planes go up. If there is a house and there is tornado, there is a house, let's say, and there is tornado above the house, so the air is moving, and when the air is moving, it has a higher speed compared to this non-moving. Here the speed is 0, here is the speed is high, very high speed of this air. Here the air is not moving, here the air is moving, flowing, so the pressure is reduced, pressure goes down. Here atmospheric pressure is big, so that's why it is a tornado which tears the roof off, but it is the difference in atmospheric pressure which produces the lifting force. So P1 is lower, P2 is increases, and that's why the difference in pressure tears the